Hello and welcome. This is sets video number 7, and today we are going to take a look at some of the collection of numbers that we have already seen in the past and how the concept of sets, subsets can actually apply to them. So now let's write some of these collections. So we know that all natural numbers, we write them as the set with uppercase letter N, and the numbers starts from 1, 2, 3, 4, so on and so forth all the way to plus infinity. So this collection of numbers are natural numbers. Then we know that whole numbers represented by uppercase letter W contains the number 0 and then all these numbers. So instead of writing all the numbers again, we can say simply n, which is the set of natural numbers. We can write this again like this. So here you can notice that W contains the set n. So we say n, we can write here n is a subset of W because W contains n. Alright, so we talked about natural numbers, whole numbers, now integers. Integers are represented by Z or Z, and they contain all these numbers from negative infinity to -2, -1, 0, 1, 2, dot, 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 all the way to plus infinity. So this collection is integers, right? So let me write over here, this is integers, because it would have been just easier if you would have got an uppercase I here, right? But that is just not the case. Next, let's find out rational numbers. Again, rational numbers is another strange letter we use, Q. Q is rational numbers, but we know what are rational numbers. Rational number is any number we can express in the form of P by Q, where both PQ are integers and Q is not equal to 0, because denominator cannot become 0, it will become undefined. So how do we write the number? Like the way here we wrote the numbers, how do we write it here? This is where the set builder form of representing a set comes in so handy. So we can write this as natural numbers collection contains element x such that x is expressed in the form of P by Q, where P and Q, they both belong to the collection of integers, which is here, which is true, but also Q cannot be equal to 0. Because if we don't put the last condition, then Q can be 0 and that will be invalid. So again, uppercase Q here, this represents rational numbers. Now we know that the next is irrational numbers, which is represented by T. I know it is very strange. And lastly, we have real numbers, which is R, which is, thank God, R for real numbers. Now, we know that real numbers basically is a collection of all rational numbers. I'm just writing it conceptually here for a moment. All rational numbers plus all irrational numbers. So that entire collection we call as real numbers. So when we are defining T, we can write this as T is such a collection that contains element x, where x belongs to real number collection, because real numbers, they contain irrational, but x does not belong to Q. See if this is making sense. Q is all rational numbers which we have defined here like this. And T is irrational. This is irrational numbers. Irrational numbers. This is T. And this is real numbers. So we are defining T as it contains x that belongs to real numbers, but the x does not belong to rational numbers. So what can we talk, what can we say about some of the sets or relationships in terms of sets and subsets? We already saw W contains n, right? So we can say n is a subset of W. We also know that uppercase letter Q is a subset of real numbers. We also know that uppercase Q is rational numbers. Also know irrational number is a subset of real numbers, right? Similarly, we can also say that we know integers, so we can say n is also a subset of z or z, right? We can say w is also a subset of z or z. So I just wanted to go over some of these relationships now that we have understood sets in some good details, and also we learned about subsets, so on and so forth. So these are things that you would not be asked directly, but some things that you must always keep in mind as we are going to look at different kinds of problems.